Hello everyone, this is Dr. Webb and welcome to this abstract algebra video where we will be focusing exclusively on polynomial rings. So let's just go over briefly what polynomial ring is. So you start with any ring R, and then we look at R adjoin X is the ring of polynomials, and so that means that every element in this ring is going to look like some f of x, which is going to equal to a naught plus a1 times x plus dot 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 up to an times x to the n. The degree of a polynomial is going to be the index of the maximum non-zero coefficient. And so this is the same thing as we talked about. You've seen degree before talking about polynomials. If the zero polynomial, so this is the polynomial where all the coefficients are zero, we're going to say the degree of that is minus infinity. I don't think that's really going to come into play with this, but there's a lot of facts about degree that make the most sense if you set the degree of the zero polynomial to be minus infinity. Now, for any other polynomial that's just a constant, so a constant polynomial would mean that f of x is actually in the ring, so it's just an element of the ring. If that element is non-zero, we're going to say that's a degree zero polynomial. But the zero polynomial has degree minus infinity. Okay, now if we take some other polynomial, let's call that g of x, then we can add and multiply g of x and f of x in the normal ways, right? And so if you add two polynomials, f of x plus g of x, all you're really doing is adding together the coefficients with the same index, right? And so that's going to give you a new polynomial where the degree of the two is usually going to be the maximum degree of f and g, depending upon whether or not there's some cancellation. Then the product of the two polynomials is what you get there, and so this is really just encapsulating what happens when you write these out and kind of do this massive foiling together. The coefficient of x to the k is going to be all the combinations of a sub I, b sub k minus I, so that's all the combinations of coefficients from a and b where the indexes of the two add up to k, and then you add those all together. Okay, so first of all, if we start off with our ring, D is an integral domain, then the ring of polynomials over D is going to be an integral domain as well. So why is this true? So let's let f of x be in d of x, and g of x also be in d of x, and these are both non-zero. Well, so then let's say the degree of f of x is equal to n, and so that means that a sub n is not equal to 0. This is the leading coefficient. Coefficient of f of x. And similarly, we can say the degree of g of x is equal to m, and so that means it has a non-zero leading coefficient, and so this is going to be the leading coefficient of g of x. Well then, if we look at f of x times g of x, well, the degree of this is going to be n plus m, and the leading coefficient is going to be the product of those two. And then plus lower stuff. And since a and n, a sub n is non-zero, b sub n is non-zero, and these are both in the integral domain, so since a sub n, b sub m are non-zero, in our integral domain in D, then a sub n times b sub m is not equal to 0 either. And so this is the leading term of the product. It has a non-zero coefficient, and so that means f of x times g of x is not equal to 0. And so you take the product of any two non-zero polynomials, you're going to end up with something that's non-zero. Okay, so now what if we move into, rather than dealing with an integral domain, dealing with a field? So we're going to let f be a field, and we're going to look at polynomials over this field. So if we take two polynomials, f of x and g of x, where g of x is non-zero, then we can do a division algorithm on them. So in particular, that means that there are unique polynomials q of x and r of x in the polynomials over f, such that we can write f of x equal to g of x times q of x plus r of x. And either r of x is equal to 0, or the degree of r of x is less than the degree of g of x, strictly less than. Okay, and so this really is talking about a division algorithm, same as we've seen with integers, for this polynomial ring over a field. So we have a division, really it should be division algorithm. And you should think about this the same exact way. In fact, it's going to have pretty much all the same properties as the division algorithm for the integers, because it's basically working in the same way. Okay, so first of all, let's talk about how this works. And so we're going to need a little lemma. And so let's suppose we have two polynomials, f of x and g of x, same as in the statement of the theorem. But we're going to set that the degree of f is at least as big as the degree of g. Okay, and we're going to let a sub n and b sub n be the leading coefficients of f of x and g of x, like we had previously. Then I can create some new polynomial from f of x and g of x, and so in particular it's going to be f of x minus a sub m times b sub m inverse times x to the n minus m times g of x, and this is going to be strictly less than the degree of f. Okay, so how does this work? So let's focus in on this guy right here, right? So we have g of x is equal to b sub m x to the m plus lower terms. So when I say lower terms, lower degree, lower powers of x. So plus the lower degree terms. Okay, and so then if we do multiply g of x by the inverse of b sub m, since b sub m is non-zero, it's a leading coefficient, so it's non-zero, and we're in a field, so it has an inverse. Every element is a unit. And so then this is going to multiply this to each of the coefficients, plus b sub m minus 1 plus the other terms. And so in particular here, these two are going to cancel off to give us a new leading coefficient of 1. And then if we then multiply this by a sub n, a sub m times what we had before, now we're going to be multiplying all of this by a sub n, and so we're going to get put an a sub n in there. Now we have leading coefficient of this being a sub n, which matches the leading coefficient of f. And so now if we multiply this by x to the n minus m, that's just going to raise the powers of all the powers of x by n minus m. X to the n minus m, g of x. And so if I raise x to the m and then raise it, well, let's write it out. It's going to be x to the m plus n minus m plus these lower terms. You can see these m's cancel off here, and so our now we have a polynomial whose degree is n with the same leading coefficient as f of x. So cleared out some space and copied out what we had at the down below. And so this polynomial is the same degree as f, the same leading coefficient. And so if we subtract them from each other, remember this is all happening coefficient by coefficient in this lead spot. We're going to have a sub n minus a sub n, x to the n, plus a sub n minus a sub n minus 1, a sub m b plus lower terms. You see that these two cancel themselves off. And so we're left with the lead term now, or possibly lead term. It's either going to be this one, maybe that one cancels off too, but whatever we're left with, it's going to be smaller than what we had before. Okay, and so this has to have degree smaller than n, and that gives us our lemma. Okay, so now let's come back to our main theorem that we have this division algorithm. And first we're going to focus in on proving the existence part of this. And we're going to prove the existence part by induction on the degree of f. And so our base case is if the degree of f is strictly less than the degree of g, so that's f of x, and this is g of x, then we can let q of x be the zero polynomial and r of x equal f of x. And so then we have that this would give us that f of x equals f of x in this equation, and we're done. Okay, and so that establishes the base case. Okay, so now for the induction step, so let's assume that if for any polynomial, let's call it p of x with degree of p of x less than k, there exists, let's call it q1 of x, r1 of x, such that p of x equals g of x, q1 of x plus r1 of x, and degree of r of x is either 0, where the degree is strictly less than g of x. And now let's let f of x be have degree of f of x equal to k plus 1, well then, using our lemma, let's let a sub k plus 1 be the leading coefficient of f of x. So then, by the lemma, if we look at f of x minus a sub k plus 1, b sub m inverse x to the k plus 1 minus m g of x, then the degree of this is less than k plus 1. So this has degree less than k plus 1. And so then it falls into our induction hypothesis. And so we can rewrite it using Q1 plus R1. So this will be equal to g of x times q1 of x plus r1 of x. And now we can just take this term, slip it to the other side, and rewrite this as f of x is going to be g of x times this a sub k plus 1, b sub m minus 1, x to the k plus 1 minus m, plus q1 of x, and then with our same remainder as before. And so there's our Q, and there's our R that we want. And so this establishes existence. Now let's prove the uniqueness. So let's suppose that we have two different ways to divide f of x by g of x. So we have g of x times q1 of x plus r1 of x and g of x times q2 of x plus r2 of x. Okay, and so now we have these two set equal to each other. And so we can rearrange this a bit. And we get that g of x times q1 of x minus q2 of x is equal to r2 of x minus r1 of x. Okay, now my claim right now is that both sides of this now have to be 0. Okay, and so why do they both have to be 0? Well, on the right-hand side, if it was non-zero, if these are non-zero, then this is the subtraction of two polynomials, both with degree strictly less than g of x. And so the degree of this side has to be less than the degree of g of x. However, on the other side, if this is non-zero, and then you're multiplying it by g of x, that can only result in the degree going up. And so this has to have degree of this has to be strictly, or it doesn't have to be strictly, q1 minus q2 could be a constant, but it has to be at least as big as the degree of g of x. And you get a contradiction here between these unless both sides are 0. And so both sides have to be 0 then, and so that means that r2 of x equals r1 of x. And then the fact that that fields are integral domains They're integral domains with every non-zero element having a multiplicative inverse. And so since it's an integral domain, that means that the only way for g of x times q1 of x minus q2 of x to be equal to 0 is if one of the terms are equal to 0. And since we know g of x is non-zero, that has to mean that q1 minus q2 has to be 0. So q1 of x equals q2 of x, and that gives us our uniqueness. And that finishes the proof. So we can do division algorithms on polynomials the same way that we do it with integers. Okay, so now we have some corollaries coming out of this. So the first two of these corollaries are going to be homework problems, and so we're not going to be proving it right now. But first of all, if we let f be a field and a be some element of f, and f of x be some polynomial over f, then f of a, so if we plug a into f, this is what you get when you, for the remainder of f of x by x minus a, right? And so if we're dividing by x minus a, this right here is degree 1, and so the remainder in division has to be degree 0, which would be a constant. And so the question is, what constant is it going to be? And this corollary says the constant's going to be what you get from f when you plug in a. So then the second corollary is same situation, but now then a is a 0 of f of x, so that's saying it's a 0 of f of x. That means f of a equals 0 is going to happen if and only if x minus a is a factor of f of x. And so what this is saying is that f of x is equal to x minus a times some other polynomial q of x. Okay, now using these two corollaries, we'll now prove this corollary, which is something probably a familiar fact that you've known for a long time, but you probably have never proven it before. So let's prove it now. And it's that if you have a polynomial of degree n over a field, then it has at most n zeros in that field, counting multiplicity. So we count multiplicity. That means that if, so let's say that if f of a equals 0 by the previous corollary, that means that we can write f of x is equal to x minus a, let's let this power be maximum, times g of x, where g of a is not equal to 0. Could just be a constant. Then we'll say this means that the multiplicity of that 0 is k. So that's what we mean by multiplicity. Okay, and we're going to do this by induction. And so let's suppose if, so the base case is degree of f of x is 0, and if the degree of f of x is 0, that means that f of x is equal to some a in the field with a non-equal to 0, because it has degree 0 and not degree minus infinity. And so then for any b in the field, f of b is just equal to a, which is not equal to 0. So there are no zeros. Okay, and so degree 0 means there's no zeros. That proves the base case. Now let's move on to the induction step. So in our induction step, we're supposing that for any p of x where the degree of p of x is less than n, that p of x has at most degree of p of x zeros, and let's let f of x have degree n, and if either f of x doesn't have any zeros, then we're done. So if it does have zeros, so if a is a 0 of f with multiplicity k, then we can write f of x as being x minus a raised to the kth power and times some g of x. Actually, let's call it q of x. Really, it's a quotient because we're kind of dividing out by x minus a to the k. By the previous corollary, that's what we'll get. And then this means that the degree of q of x is going to have to be the degree of f minus this power k. So it's going to have to be n minus k, which is strictly less than n. And so by the induction hypothesis, q of x has at most n minus k zeros with multiplicity. And so then that means that f of x has those zeros plus k more. So f of x has at most n minus k plus these k more, which is equal to n zeros. And that finishes the corollary. So we're going to spend the last bit of this video proving a very important fact about polynomial rings over fields. And so it's going to involve principal ideals, which we've seen before when we've talked about the integers. And so remember, a ideal is principal if it's generated by a single element in the ring. We say that a ring is called a principal ideal domain if it is a domain where every ideal is principal. So every ideal can be written as a times all the elements of the ring, right? So just recall that this ideal generated by A, this is A times R, where R is ranging through all the things in, not the real numbers, the ring. Okay. And so for a principal ideal domain, every ideal can be written in this form in some way. So the important fact about polynomial rings over a field is that f of x has to be a principal ideal domain. And so it's critically important that this is a field. If it's just a domain, not a field, then this is no longer true. But if we're working over a field, then f of x has to be a principal ideal domain. Okay, so let's let I be an ideal in f of x, and let's choose g of x in this ideal to be non-zero with minimal degree. Okay, and so this is the fact that we can choose this g of x comes from the well-ordering principle. So if we look at all the non-zero elements of this ideal, well, their degrees of these are all going to be either 0 or a natural number. And so that means that there has to be, so we can look at this set of degrees in this ideal. And since it's just 0 in the natural numbers, that means that there has to be a smallest element in there. And so we're just going to take g of x to be, there might be more than one such g of x, and we're just going to take g to be one of them. Okay, now my claim then is that I is going to be generated by this g of x. And so the proof of this is let's let f of x being the ideal, then note that since g of x has minimal degree, let's let f of x be non-zero. Then this means that the degree of f of x is at least as big as the degree of g of x. So we get this because g of x has minimal degree for elements in here. And so then we can divide f of x by g of x. And we get that f of x is equal to g of x times some q of x plus r of x. Now this r of x, if the r of x is non-zero, well, since f of x and g are both in the ideal, that means that f of x, we'd have that f of x minus g of x, q of x, is in the ideal. And so that would be r of x. But r of x has degree strictly less than g of x. And so that would contradict that g of x had the minimal degree. And so that would, so if r of x is non-zero, this contradicts g of x has minimal degree. So this means that r of x has to equal 0. So we conclude f of x is equal to g of x times q of x. Since f of x was any non-zero element of the ideal, that means that any non-zero element of the ideal can be written as g of x times something. So we can conclude that I is the ideal generated by g of x. And that finishes the proof. Okay, and then looking at this, at how we prove this, we actually proved a bit more, and so we'll write that bit more in the corollary. And so that if we have some non-zero ideal in our polynomial ring, then we take any non-zero polynomial of minimal degree in there, then I is going to be generated by that polynomial of minimal degree. And so even if there's multiple polynomials of minimal degree, that means that each one of them can be written as a product of the other one. And so since they have the same degree, that means that they just differ by a constant. So if I equals g1 of x equals g2 of x, so these are two polynomials of the same minimal degree in I, well, this means that g2 of x is equal to g1 of x times something. But since these g2 and g1 have the same degree, that means that the degree of this has to equal 0. So q of x is equal to some a in the field. And so any of these polynomials that generate the ideal are just going to be another one times some unit, times some element of the field. Okay, so all of these minimal polynomials, in fact, there's going to be as many of them that generated as there are elements in F. So if F is an infinite field, that means there's infinitely many of them, but they're all just going to differ by, they're all really going to be multiples of each other by some constant in the ring. That is all for this video. I will see you again soon.